Swayam Prabha. Digital India. Educated India.
So, the last few lectures we looked at instrument transformers, current transformers and voltage transformers. Today we will start a new topic which is symmetrical components. Before going on to symmetrical components, we will have a quick look or a revisit to per unit quantities and per unit calculations. This is you must have done this topic in some of your other courses or subjects, but it is worth repeating that just for the sake of for refreshing your memories, as also re-emphasizing the usefulness of these per unit calculations. Okay, so we will have a quick look at the per unit calculations. We will solve a few problems from a textbook which is purely devoted to symmetrical components. It is titled Symmetrical Components for Power Systems Engineering by J. Lewis Blackburn. There are quite a few problems on symmetrical components and also per unit calculation. There is one chapter devoted to per unit calculation. So, we will solve a few unsolved problems from there, so that you get a better look at this per unit calculations, or rather these per unit calculations. Okay, so as we can see on the screen, the by definition a per unit quantity is defined as actual quantity upon base quantity. So, it could be per unit voltage, per unit current, per unit impedance. The basic concept is a per unit quantity is the actual value of the quantity divided by whatever base quantity that you have defined. Now, it is also a percent calculation is also used. It is analogous. You just multiply the per unit quantity by 100, you will get the percent quantity. So, as we can see, it is per unit of the base. So, that is why it is the system is known as a per unit system. Now, the base current and the unit is amperes is defined as base kVA, whatever base you define. Many a times for convenience we define 100 MVA as the base, but that is not necessary. Anything can be defined as the base. So, base kVA into 1000 or base MVA directly divided by root 3 into base volts. Okay. Base impedance in ohms is base voltage divided by root 3 into the base current. Okay. So, this is these are the base quantity definitions. Then per unit for Z or the impedance in per unit is actual impedance upon base kV square, and that divided by base MV, which is the in other words base kV square divided by base MV is nothing but the base impedance. So, actual impedance upon base impedance will give you the impedance in per unit or Z per unit. Okay, why we will look at a few problems, but before that, why is per unit or per unit calculation or per unit calculations so widely used? That is because a few advantages which are listed in the slide here, that manufacturers generally provide them with equipment with nameplate or what is known as nameplate rating is that is the base. Okay. So, and if they are not available, then the range is quite easily available. You know, transformers, for example, transformers above 10 MVA or 12 MVA as per the IS will be around 12.5% or 0.125 per unit Z. Okay. So, if you don't know the ratings or you don't know the impedance values, then you can use tables which are there in textbooks or some literature like papers, etc. So, also where there are multiple levels, like in your transmission system there will be maybe 33 kV, then 110 kV or 220 kV, 400 kV. So, multiple levels which are connected to transformer through transformers. This per unit system is particularly useful, otherwise you have to do the impedance transformation depending on the turns ratio, etc. One important thing to note, and we will see that in the problems that we solve, is that per unit impedance of a transformer is independent of the kV base. Okay. So, whether you refer to it as primary kV or secondary kV, the kV base, the per unit impedance of the transformer is the same. Okay. And standard base conversion formula are available, which we will see shortly. Okay. So, let us go to a few problems. We will list these quantities again, and then we will look at a couple of problems for a transformer ZPU is equal to, say, Z actual upon Z base, which is nothing but Z actual upon kV square, and that divided by MVA. So, that MVA you can take here. So, this is the Z in PU. Now, how do you change the base? Because this may be available in a particular base. Now, you have decided you need a different base, or you have the equipment is given on its own base, the values are given on its own base, and for the whole network you say choose a base kV of say 220 kV and 100 MVA base. So, how do you change? So, Z per unit new is equal to Z per unit old into kV square old upon kV square new into MVA new upon MVA old. Okay. So, this is how you will change the base. Now, we will have a look at a couple of problems, two problems, and then move on to the actual topic at hand, which is symmetrical components. Now, this is the first problem. The circuit is given as follows. This is a generator with a 25 MVA generator. This is an American textbook, so the values may be a little unfamiliar, but in terms of the voltages, etc., but the principles remain the same. So, this is XD double dash is we will see what are the ranges of XD double dash, etc., but before that we will just have a look at the per unit system. So, this is 25% or 0.25 pu. Okay. So, usually they are given in percentages, but I mean it is just a factor of 100. So, this is a bus, this is a transformer, a delta star grounded transformer. This is another bus here, and then it goes to the system. Okay. So, this transformer is rated as 30 MVA, 4.2 is to 115 kV. As I said, this is an American textbook, so the operating voltages could be a little different. Operating on 3.9 kV tap. Okay. And XT, the transformer leakage impedance, is 10% or 0.1 pu. Okay. So, now we want to convert it into a common base. So, how do we proceed now? The problem given is they have to be converted into a single equivalent reactance. The common base could be chosen to be either, I mean 25 MVA or 30 MVA, and then we could have converted it to that. But here we have been specifically told that we need the common network impedances on a 100 MVA and 110 kV base. Okay, so these are the base quantities that have been given to us. So we need to convert the above two to these base quantities. Now the transformer is operating on a 3.9 kV tap. So the ratio is effectively 3.9 is to 115 kV. If it were to be fed with 110 kV voltage instead of this 110 instead of 115, then what would be the voltage on the LV side? So we have kV on the LV side divided by 110 is equal to 3.9 upon 115, or in other words, kV LV is 3.73 kV. Okay. So this is what we get. Now what have we been given? XT is equal to 10%, but you have to remember that this 10% is on a 3.9 kV 30 MVA base. Okay. Now we have to convert it into a 3.73 kV 100 MVA base. Okay, these are the old values, these are the new values. Okay, so XT, JXT in particular, but we are dropping the J for convenience, is equal to 0.1 because it is given as 10% into kV square old. So what is the old kV square? 3.9 divided by kV square new 3.73 square into what is the MVA new? 100 divided by 30, which will give us, I just solved it. So this gives us 0.364 per unit. Okay. On a, so 364 per unit is on what base? Because we have to specify that is on 3.373 kV 100 MVA base or 110 kV 100 MVA base. Okay. Similarly, now the voltage on the primary side is 3.73 kV. So the generator base was given as 4 kV. So we need to convert the generator XD double dash also. So we will do that. The GA XD double dash, again we can drop the J for the sake of convenience, is 0.25 into 4, because 4 is the kV old, divided by 3.73 square, which is the new kV base, into 100 new MVA base divided by 25. So this will give us 1.15 per unit. Again on 3.73 kV 100 MVA base, or equivalently on 110 kV 100 MVA base. Okay. So what is the total reactance that we set out to find? It is X total is 1.15 plus 0.364, I am sorry, per unit is 1.514 per unit, or 151.4 percentage on again same thing, 3.73 kV 100 MVA base or 110 kV, both are equivalent. Okay. So remember that since there is a transformer, the base on either side can be taken. Okay. So, we will have a look at one more problem, so that the concept is nice and clear. We will not solve the whole problem. I will just will tell you the method of the solution, and then maybe you can solve it yourself. This is problem 2. Two transformers are connected in series. One transformer is rated is rated 15 MVA and the voltage ratio is 66:132 kV and X is 10%, and the second transformer or the other transformer is a 10 MVA, 13.8 is 69 kV, 8% X. Okay. Determine the reactance of each transformer and the total reactance sum of two in series in percent. Percent or per unit does not matter, you can simply multiply by 100 on a 30 MVA 138 kV base. Okay. The problem is interesting, and it will also point you to some pitfalls that should be avoided. Okay. So, we will just draw a quick network. So, these are two transformers in series, okay. And what is the first one? 66 is to 1, we will draw this as 66:132 kV, and what is it? 10% and 15 MV. Well, this transformer here is 13.8 on the LV side, 69 on the HV side, and 8%. Okay. And now we have, our problem is to find 138 kV. This is a new base. 138 kV and 30 MV. Okay. So, for the first transformer, this one, this transformer, what will it be? X new, or we can say X1 new is 0.1 or 10% or 0.1, whatever you choose. Since it is asked to, the answer is required in percent, we will keep it at 10%. So, 10% into kV old. So, 132 is the new old kV upon 138 square into what is the new? 30 by 15. So, this is 2 and whatever value you get here. Okay. Now, here, well, this is quite straightforward. For the second transformer, you will not use say x2 nu is equal to 8% into what is it 69. You will not use 69 square by 138 square into what is the MVA given for this transformer. This is a 10 MVA, I am sorry, this was not mentioned here, 10 MVA into 30 by 10. So, this is wrong. Okay. This is a very common mistake which is made and which is wrong. What you need to instead do is, you need to, if the base is given as 138 here, so what will be the value on the LV side of the transformer 1. Okay. So, we will have kV LV of transformer 1 divided by 138 is equal to 66 by 132. Okay. So, whatever value that we get here, some 67 or 68 kV approximately, let us assume. Okay. I have not done this calculation unlike the earlier one, but you can please do it here and see. So, x2 nu will actually be now 8% into 69 by 68 square into 30 by 10. So, this is a mistake which has to be avoided while making this, while you do this PU calculations or per unit or percentage calculations. So, be very careful when you are doing these calculations, and especially involving transformers. So, that is why we took two problems here, so that the concept is clearly brought out. Okay. So, now we will move on to having had a look or maybe a revision of our per unit concepts. Now, we will move on to the topic of symmetrical components or sequence components, or as they are also known as. Okay. So, why do we primarily, as protection engineers, why do we require sequence components or symmetrical components? The basic reason is that we need to have an insight into the nature of the fault and how to set our relays. From a purely computation viewpoint, sequence components are no longer necessary. You can actually do all the calculations, all the fault calculations in the phase domain itself, and unless you are doing it by hand or so, where we will see that in probably the next lecture, how we calculate the fault currents, etc., by sequence transformation. We transform the networks and decouple them into positive, negative and zero sequence components, and then our calculation by hand becomes easier. But from computation, where you use modern computers to calculate this, it is no longer necessary. But as a post-mortem tool or as an analysis tools for a protection engineer, it is invaluable. So, that is why we will study this in some detail. So, let us move on. The basic, as we said, the basic value of this is in the calculation of fault currents. Why do you need to calculate the fault currents in the first place for a protection engineer? Is that you need to know the values of the fault current and the impedance for setting your relays, and also the coordination. The equipment rating on a broader perspective, not just a protection perspective, the equipment rating also has a short circuit rating. So, it should not fail on that, because the electrical and mechanical forces are quite high. So, that is why the equipment short circuit rating is also specified. So, we need to calculate the fault currents for both these purposes. Okay. So, the fault current, basically the fault current in a power system network usually comes from synchronous machines, which are our generators, or synchronous machines or synchronous motors, Then there are induction machines which are used. Quite a lot of our load, especially industrial load, is induction machines. The contribution, though not in terms of time, though not as not as high as synchronous machines, but there can be a significant contribution. Many times it is ignored because the contribution is only up to a cycle or so, or a couple of cycles. But for a detailed calculation, even that can be considered. Then of course, the electrical utility, if we are considering on from a pure fault perspective, whatever is your transmission network is also contributing to the fault. And nowadays we have distributed generation in terms of solar, wind, maybe even diesel generator. So whatever is the distributed generation in the system can also contribute to the fault. Now coming back to our sequence components, this was a concept which was introduced by Charles Fortescue, who was with General Electric at that time, and it was introduced more than 100 years ago, in 1918 to be precise. His first paper came out in 1918, and as with all good ideas, has survived the test of time. We still use sequence components. You can imagine this was there. It has been there since almost the beginning of electrical power networks. Okay, so what was his intuition behind this? It was that, if you have a single phasor, how many degrees of freedom do you have? I have a single phasor like this, so I can place it anywhere in space, and also the magnitude is in my hands. So I have got 2 degrees of freedom. One is the length and one is where I place it. Okay. So similarly, if I have a 3-phase unbalanced system, how many degrees of freedom will I have? So if I have a 3-phase unbalanced system, now this is my A phase. I am not deliberately not writing voltage or current because it could be anything. B phase and say another C phase. So how many degrees of freedom here? 6 degrees of freedom, right? Because each of them can have different magnitude, as well as can be placed anywhere in anywhere in space relative to each other. So there are 6 degrees of freedom. Okay. However, if this system were balanced, say I have a balanced 3-phase system. Okay, this is what we are very familiar with. The phasor magnitudes are equal, A, B, C. They are assumed that they are equal, though they may not appear to be same in the drawing. 120 degrees and equally spaced apart. Okay, so they are placed equally apart in space. So this is a balanced system. This, on the other hand, was an unbalanced system, which had 6 degrees of freedom. This is a balanced system. How many degrees of freedom does this have? It will have 2 degrees of freedom. Okay, because once I fix one magnitude and its position in space, the other 2 will get fixed. Okay. So the intuition and the brilliant intuition of Fortescue was that a system like this, a 3-phase unbalanced system with 6 degrees of freedom, can be replaced by 3 such systems with 2 degrees of freedom. Okay. So what they are, we will see shortly, but we have 3 balanced systems which can make up a single unbalanced system, one unbalanced system. Okay. Now note that this is applicable, 3 balanced systems is applicable for 3-phase systems. Okay. When Fortescue published his paper, it was for an n phase system. Okay. So, it is equally applicable for higher order phase systems also. It is not that it is limited to 3 phase systems. Why n phase? Because that time 100 years ago or more than 100 years ago, there was still a debate of whether we should the power transmission should be at 3 phase or 6 phase, or So, this discussion equally holds true. When we see the components, I will also tell you what will exist if the phase number is higher or the phase order is higher. What the 3 balance systems are as follows. The first one is the positive sequence. Okay, this has the same phase sequence as that of the original system. Okay, so this is say now we can say this is the VA, VB, VC. The positive sequence, we can write it as positive sequence here, has the same phase sequence as the original system. We will introduce an operator here, A, which is 2 pi by 3 or 120 degrees. Okay. So, VB here can also be written as A inverse, because we take the rotation in the counterclockwise direction. Okay. So, can also be written as leading by 240 degrees. So, VA plus. Okay. And similarly, VC is leading by 120 degrees. So, VA positive is A into VA plus. Okay. And VA plus is of course VA plus. I am not writing it is quite. The second sequence component is what is known as a negative sequence component. This is also placed 120 degrees apart in space. However, the sequence of rotation is opposite to that of the original system. So, if the original system was ABC, this will be ACB. So, VA VB negative. Okay. So, here A into VA negative and VC is equal to A square into the third sequence component. We said that there will be 3 sequence components, and therefore, the third sequence component will be what is known as the 0 sequence component. Okay. Here the 3 phasors will be equal in magnitude. However, the phase angle or the phase angle separation between them will be 0 degrees. Okay. This is also fits our definition that they are equal in magnitude and equally placed apart in space. Okay. So, that is an important part of the definition, equal in magnitude, which is fulfilled by all of these. Okay. So, here equal in magnitude and equally spaced apart or equally placed apart in space, either you can use either of the. So, here what we have is VA 0 equal to VB 0 is equal to VC. Okay. Now, this can be written in a compact matrix form. VA, VB, VC is equal to, in terms of its sequence components, this is VA 0, VA 1, VA 2. So, here it is of course 1, 1, 1, because VA is equal to VA0, I will write it in. Plus VA1 plus VA2. Similarly, VB is VB0 plus VB1 plus VB2, which can also be written as VA0 plus A square VA1 plus A VA2. Similarly, VC can be written as VC0 plus VC1 plus VC2, which is the same as VA0 plus A VA1 plus A square VA2. So, in a compact form, we can write this as 1 A square A 1 A square. Okay. The thing to note here is that we are using A as the reference phasor here. A is used as a reference phasor. If you use B as the reference phasor, this matrix will change slightly, I mean the rows will permute. So, you can do that for yourself and see what happens if you can use this as an assignment. How we will name this as the T matrix. Okay. Rather than what, I will use the word how. How will the matrix T change if we use B as the reference phasor? Okay. This is an assignment for you. Please try to solve it by yourself. Okay. Now, one thing which is to be noted is that whatever be the phase of the system, if it is 3 phase, 4 phase, n phase, positive and 0 sequence components will always be there. Okay. What in between, if it is a 3 phase system, you will have 1 sequence component in between, because there has to be 3 sequence components. So, you will have the negative sequence component in between. If you have a 4 phase system, you will have 2 sequence components in between. If you have a 6 phase system, you will have 4 sequence components in between. So, positive and 0 sequence will always be present. 0 sequence are always present, and okay. And then depending on the phases of the system, you will have multiple sequence components. Okay. So, just quickly look at how a 4 phase system would look at, just for the sake of interest. We do not have a 4 phase system anywhere. So, say A, this is our 4 phase system. I mean phasors of a 4 phase system would look like. The positive sequence would be the same as the original system, A1, B1, C1, I am sorry, D1. Okay. The second sequence component would be A2, then we have B2, then C2 and D2. The magnitudes are equal. Okay. The thing to note here is that the B has changed by an angle n into 360 by the number of phases. Okay. So, this is the second sequence component. The third will be A3, B3, and finally, the 0 sequence components will all be A, B, C and D, A4, B4, C4 and D4. Okay. So, this is how a 4-phase sequence components of a 4-phase system would look like. Okay. So, this is what we discussed. A set of unbalanced 3-phase phasors can be synthesized from 3 sets of balanced phasors, and they are known as positive, negative and 0 in the 3-phase case. Okay. We had a look at these also. This is how diagrammatically they will look. We will quickly go through these slides just to make sure that we do not miss anything. And the 0 sequence, the final one is the 0 sequence component. Okay. One thing is, if you apply negative sequence components to a induction machine, what will happen if you change the phase sequence of supply to an induction machine? It will rotate in the opposite direction to what it is normally rotating. If you take the normal rotation as viewed from the driving end as anti-clockwise, then in this case, if you give a negative sequence excitation, it will rotate in the clockwise direction. However, if you give 0 sequence excitation to an induction motor, then there will be no rotation. That is because no rotating MMF is produced. Why is that? We will just see mathematically why why 0 sequence currents produce no rotating MMF. Now, if you see MMF distribution, you will just write down the formulae and then plug the sequence currents into them. MMF distribution in A phase winding is given by say F A. F is the MMF notation for MMF. So, N number of turns into I A into cos of theta. Okay. Theta is the angular displacement. For the B phase winding, MMF distribution for the B phase winding, I am not writing the whole thing again, but B phase is given by, it will be the same, but displaced by 120 degrees. Okay. Balanced. And MMF distribution for C phase is given by FC is NIC. IA, IB, IC are the currents in their respective ABC phases. Now, what is the net MMF in the gap? It is given by F net is equal to FA plus FB plus FC. These are phases, of course. Now, suppose the currents were to be positive sequence currents. So, what is the what is the mathematical expression for the MMF wave due to positive sequence currents? Okay, we will substitute positive sequence currents in the above expression of MMF. Okay. So, for positive sequence currents, so let say I A positive is equal to I m cos of omega t So, IB positive will be cos of omega t minus 2 pi by 3, since it is balanced and displaced by 120 degrees, and IC positive is Im cos of omega t plus 2 pi by 3. Okay. So, if we substitute these three currents in this expression, F net expression, then we will get F net positive sequence, which is a function of both time and theta. We just substitute and manipulate the trigonometric identity, we will get 3 n Im cos of omega t minus of theta. Or plus theta. Okay. Oh, I am sorry, it will be minus of theta. Minus of theta. Okay. For negative similarly for negative sequence currents, say let I negative is I can be the same as before, I am cos of omega t. IB negative is I am cos of omega t plus 2 pi by 3 in this case, and IC negative is I am cos of omega t minus 2 pi by 3. Okay. So, F net negative, therefore, substituting in the above expression, F net negative as a function of t and theta will be 3 by 2 n I m cos of omega t plus theta. Please do it for yourself and verify once. Okay. And the last will be MMF wave due to zero sequence components. Okay. So, here let since they are all the same, I A 0 is equal to I B 0 is equal to I C 0 is equal to I m cos of omega t. So, if you substitute these three currents here in this expression F net, then the resultant will be T of theta is equal to 0. Okay. So, that is how you get the resulting MMF wave to be 0. So, if you excite induction machine with zero sequence currents, then you will get no rotating magnetic field. Okay. So, we have seen the sequence components. If you see here, unfortunately this is not animated, but you can see here how the set of unbalanced phasors, the red, yellow and blue is the unbalanced three phase set, and that is now made up of positive, negative and 0. Okay. So, you can add the three components appropriately. If you see here, you can see A1 plus A2 plus A0 will give me the A component. Similarly, B1 plus B2 plus B0 will give the B, and C1 plus C2 plus C0 is giving me the C component. So, this is how unbalanced set of phasors can be synthesized from a balanced set of phasors. Okay. Now, the thing to be noted is that this transformation here from the sequence domain to the phase domain is a linear transformation. All properties of linear transformation apply. Now, how is that? That is because you have this T matrix to be a constant matrix. This T matrix is a constant matrix, and also it is an invertible transformation. Okay. So, why is that? You can verify this, and the invert, you do not have to actually find the inverse. What is it, our T matrix? 1 1 1 1 a square a 1 a square. Now, it is made up of all constant elements, and also the thing to note here is that the rows and columns are orthogonal to each other. Okay. So, we have say if x I and x j are the rows, then x I transpose conjugate x j is equal to 0. Since this is a complex matrix, these entries are complex. If the entries were real and the rows and columns are orthogonal, you will simply get x or x I or x I transpose x j is equal to 0. But since they are the entries are complex, we need to do a conjugation also. Okay. So, the inverse is quite simple. T inverse is 1/3 1 1 1 1 a square 1 a square b. Okay. This 1/3 comes because the length of these columns and rows is not 1, but root 3. So, that is why this you get a 1/3. In other words, the columns are orthogonal to each other, but they are not orthonormal. Okay. So, that is why you get the factor of 1/3 here. Okay. And since you can go from one domain to the other without any loss of information, it is also known as a linear. It is also a linear transformation, and it satisfies all the properties of linear transformations. Okay. You can verify that once. So, you go from this is the first transformation is to go from the sequence domain to the phase domain, and inversely to go from phase domain to sequence domain, you use the bottom transformation. Okay. Say you do your calculations in your sequence domain, and then you want to get back the phase because you need to look at the phase current. So, then that is why you may need to go the inverse way also. Sometimes it is just sufficient to calculate the sequence components and be done with it. Okay. So, we will move ahead. This is the inverse transformation. You can see that from an unbalanced system, we have an unbalanced system and we are getting the sequence components out. Okay. So, the factor of 3 is there because, as we said, the columns are orthogonal, but not orthonormal to each other. So, A, B and C combined will you have synthesized the positive sequence component, you have synthesized the negative sequence component here, bottom right corner, and also the 0 sequence component. Okay. So, as we discussed, the transformation is linear, and it provides us a method to convert sequence domains phasors to phase domain. As we said earlier, from a computation standpoint, there is not much to be gained by doing your computations or fault current computations in the sequence domain. You can as well do it in the phase domain. The computers are powerful enough to handle that. It is only the insight that the sequence domain transformation gives you that is the reason why we still persist with it, not only from not just from a computation viewpoint. So, there, as we said, since it is a linear transformation, there is no loss of information from while going from one domain to another. Okay. And both the transformations in themselves are linear. Okay. So, we will have a quick look at modeling in the sequence domain before we stop. Here the value of the sequence transformation is brought out when the network is balanced. The load may be unbalanced, but the network is balanced. Okay. So, we will see this network modeling in the next lecture.